We've shown that B implies C in the invertibility theorem, so now let's show that C implies D. In other words, if the homogeneous linear system has only the trivial solution, then the rank of A is equal to n, so C implies D. So consider a generic homogeneous system. Consider the homogeneous linear system. Well, generic, but with n equations and n variables. So we'll write it like this: a11 x1, a1n xn equals 0. And I'll write the last equation, an1 x1, all the way to ann xn. Remember this from chapter 3. This is the way we write a generic linear system. And we'll say that if the system has only the trivial solution, if the system has only the trivial solution, and of course the trivial solution is x1 equals 0, x2 equals 0, and so forth until xn equals 0. But if this is the case, right, if we're going to have this as the only solution, then the augmented matrix, well, we know how it's going to turn out. The augmented matrix, which looks like this, a11, a12, a1n, 0. We'll write the first two rows, a21, a22, a2n, 0. And the last row, an1, an2, ann, 0. So this augmented matrix of that linear system, well, it has to turn out in the following manner. Will be reduced through row reduction to the following, right? There will be no choice. It'll turn out like this: 0, 1, and the last row, the last row here will have a 1 and 0. And so inevitably, if the system is to have only the trivial solution, then we have to have 1s on that diagonal and 0s everywhere else. We're used to this. But this, of course, means that the rank of A will equal n, right? Why is that? Well, it's because this matrix on the left, this is the matrix A, and if the augmented matrix reduces to this, it means that it'll reduce to this matrix. And this, of course, has n columns, and therefore, since each column and each row has a leading 1, there are n leading 1s, and that's the rank. And so we've just proven C implies D. So let's prove D implies E. And this is, well, basically we can see it right here, that if the rank of A equals n, then, or actually let's say, and let's give the reduced threshold form a name, we'll say R equals the RREF of A. Well, then what's R? Well, R is an n by n matrix with n leading 1s, right? With n leading 1s. In fact, it's basically the matrix that I highlighted in yellow above. Why n leading 1s? Well, because the rank is literally the number of leading 1s in the RREF, in the reduced echelon form, so that matrix is R, with n leading 1s and 0s everywhere else. 0s in every other position, because, well, to qualify for to be RREF, it needs to have 0s above and below those leading 1s, and therefore, since there are n columns with n leading 1s, everything else will be 0. So 0s in every other position. Sorry, I should have said in every other position. And therefore, conclusion is that R has to be the identity matrix, right? And therefore, A is row equivalent to I. And that's exactly what we wanted to show. And then the last implication, just to close the loop, which is E implies A. In other words, if A is row equivalent to I, then A is invertible. Well, this, we've seen how it works, but we'll just write it a little bit more formally. So we'll say if A is row equivalent to I, then there's a sequence of elementary row operations. There exists a sequence of elementary row operations, that sequence turns A into I. Right? That's what it means for A to be row equivalent to I, i.e. A will apply, let's say, the first operation, let's say O1, gives you A1, and so forth, until we'll apply the last operation, which produces I. But we saw, and I'll write it here, we saw that that same sequence, and here I'll have to say we saw but did not prove formally. So a little disclaimer here, but did not prove formally. So we saw that the same sequence turns I into A inverse. Okay, so I'll just borrow a little space on the following page here. Turns I into A inverse, and therefore, or actually here before I write my conclusion, I'll just remind you that that means I, with the same operations, will simply turn into A inverse. Okay, so that same sequence of operations that turns A into I will turn I into A inverse. So we haven't proven this formally, but we've seen enough examples to be convinced that this is true. So if we were to really complete this proof in a formal manner, we'd have to show that step. Okay, but this will be enough for the purposes of our course. And therefore, since this sequence turns I into A inverse, we'll simply say, therefore, A inverse exists, and therefore, A is invertible. And that concludes the proof of the invertibility theorem.